Yeah, the last two problems were different than the first two. Alright, so let's assume that G is 10 meters per second squared. That's constant, so we can write that across the board. Let's go ahead and get heights. So what's the height at point A? What's the height at B? Are you sure it's unknown? We can, this dashed line means that's 60. What about C? What about D? And what about E? So again, they sometimes hide information, like this dotted line is supposed to represent that they're at the same height. We can also look at potential energy and tell that they're at the same height from potential energy. So let's look at velocities. So all we're given is kinetic energies. If your kinetic energy is 0, what does it tell you about velocity? It's 0 too. And let's go ahead, it gives you kinetic energy. So kinetic energy is 0 and potential is 50,000. And total would be 50,000. And it's constant, so go ahead and just write that down as soon as you first get it. We'll see on the next problem. Make sure you read the description first. So B, kinetic energy is 20,000 and potential is 30,000. At C, it's 35,000 and potential energy is 15,000. And D, 20,000 and 30,000. And for E, it's 50,000 and 0 joules there. Alright, so we have all of our energies. From our energies, we can get the rest. So we know mass is constant, so let's just get mass out of the way. So we have multiple formulas for mass. We can use kinetic energy to solve for mass. So mass would be equal to yep. It's not yes. So but this is my point. So mass is equal to 2 times the kinetic energy divided by velocity squared. Now note, kinetic energy is 0, so 2 times 0 is 0. 0 squared is 0. We end up getting 0 divided by 0. Can we divide by 0? No, so we can't use this equation for solve for mass. So let's look at our now other equation. Our other equation for mass is potential energy. So mass is equal to potential energy divided by gravitational acceleration times height. So you can use either one of these. However, if your velocity is 0, you can't solve for it. If your height is 0, so for example, coming over here, we can use mass is equal to potential energy divided by GH. So our potential energy is 0. 10 times the height of 0, we get 0 divided by 0. We can't divide by 0, so we can't use this equation. Over here, though, so reason why we have to check. If we get a divide by 0, we can't use the equation. Because math says we can't divide by 0, so we can't use it. For this one, potential energy is 50,000. And we're dividing by 10 times a height of 100. So that'd be 50,000 divided by 1,000. Right? So 50,000 divided by 1,000. That's just 50 kilograms. So we can come over here and put 50 kilograms. Again, we can assume mass is constant. We could also have used any other point. So let's try using this one to solve for it. So mass is equal to potential energy divided by gravitational acceleration times height. Here is 30,000 for potential energy. G is 10. Our height is 60. So that'd be 30,000 divided by 600, which is equal to 50 kilograms. We get the exact same number. So this tells us that our mass is constant. Now let's solve for velocity. So remember that velocity is equal to the square root of 2 times the kinetic energy divided by mass. So velocity for part B would be equal to 2 times 20,000 divided by 50. So that would be the square root of 40,000 divided by 50. Remember to put a decimal point somewhere so your calculator will get you the correct answer. And that'd be 20.28427. So we can plug that in. 20.28427 meters per second. For this problem, we can do the same. So 2 times the kinetic energy is 35,000. The mass is still 50. And we get a speed of 37.41657 meters per second. And we can do the same thing for this. So velocity is equal to the square root of 2 times kinetic energy, 20,000. No! Do these have the same kinetic energy? That means they have the same speed. If the kinetic energy is the same, we don't have to redo the calculation because it'll work out to be the same. Is this 2 times 20,000 divided by 50? So these are the same numbers. And for the last one, speed is equal to the square root of 2 times kinetic energy. So 2 times 50,000. Divided by mass of 50. Make sure you count the number of zeros. That seems to be the number one problem, is people are not putting the correct numbers into the calculator. And we get like where 44? Oh yeah. Yeah. So let's look at this. Let's look at the speeds versus heights. So over at A, the speed is 0. Once we go down, our speed increases to about 20. Then we go down and it goes to about 37. We then go up higher, it decreases to 20. And then we go to the very lowest point and we're now over at 44, close to 45. So the farther closer down to the ground, the more kinetic energy you have. So this would be the fastest point. And the higher up you are, you're going the slowest. So when you're going the fastest at the bottom, so you have high kinetic energy. And up here at the top, you have low kinetic energy. Let's look at potential energies. So when the height is high, your potential energy is the highest. As you start going down, you start losing some potential energy. That potential energy, so when we go from 100 down to 60, we lose 20,000 joules. Where does that 20,000 joules go to? So 20,000 goes into kinetic. Once we drop down lower, so we lose another 15, that 15 goes into the kinetic energy. So the sum of these two are constant. We're just converting between potential and kinetic energy. So compare the first one and the last one. The first one we had no kinetic energy but 50,000 joules of potential. At the bottom, all the potential energy is converted into kinetic. This is the fastest speed you can reach. So is everyone good? The last problem is the most difficult. Yes, it's supposed to be. So let's read carefully. An 850 kilogram roller coaster is released from rest at point A of the track shown in the figure. Assume there is no friction or air resistance between points A and C. I should write also. There is friction between C and D. Now, remember what I said, so let's go back up. In the absence of friction, total mechanical energy is also conserved. It's the energy from motion and position alone. If we include friction, total energy is still conserved, but mechanical energy is not. Some of the energy is going to be converted into thermal energy, heat. So the mechanical energy will be lost between C and D. So we can't use our problem-solving technique for point D. Only between A and C can we actually use this table to help us solve. So I'll still write into this, but just to help us out, this is going to be wrong. Because between C and D, there is friction, we can't use this table to help us solve it. She is. Alright. So let's go ahead and do what we know. Mass is constant. So 850 kilograms. Does friction cause mass to change? So we can go ahead and put it in the D. So point D has friction. We'll assume that G is 10 meters per second squared. So we'll don't just scribble it because I'm still writing the numbers in. Yeah, friction. I'm putting the X. You can still read my numbers, and you can do the same thing. I'm not going to give a problem like this because it's more difficult than others. I'm putting the X as a reminder. that I can't, and Cody and everyone, make sure you're wearing a mask. I'm putting the X here to help remind me that this is different. That every single time I get to point D, I have to ask, does friction affect it? So, acceleration to gravity is 10 meters per second squared. 10 meters per second squared. Does friction affect gravity? Air resistance. So we have air resistance. So air resistance can affect rate of fall. However, our equation doesn't count for air resistance, so it is still 10 meters per second. It doesn't apply in this case. Mm-hmm. It'll slow you down. But note that in this case, when we look at gravitational potential energy, this value is gravitational only and not your total acceleration. So we can put 10 meters per second squared here. So in this one example, this G doesn't matter because you're sitting on the ground. It's sitting on the track. Now, what this would change is this problem. When you're no longer on the track and you're falling downward, you have gravity pulling you down, but you have air resistance pushing you back up. Here, when you're sliding on the track, there's no air between you and the track. Again, I crossed this out because we don't really need to be filling this out. So let's do height. What's the height at point A? 140 meters. At B, 94 meters. At C, 80 meters. And the height doesn't depend on friction. We can plug that in. I meant 95. Sorry, I was reading it off and said one thing. So, assume that it is released from rest. So what does that tell us? No velocity and no kinetic energy. Yes. So potential energy. If you're standing on ground, if you're stopped on the ground level, we would say that your total mechanical energy is 0. Again, technically energy is relative. You could be sitting at infinite energy. We only really concern ourselves with differences. We set some arbitrary value to be 0. We usually set the surface of the ground to be 0. It's arbitrary. Because technically, if you dug a hole, you now increased it, and you can jump down in the hole. And remember, you can't create energy, so by digging a hole, you're not creating new energy for you. It's just that we just happen to define that's where 0 is. You would have to readjust where you define 0. So the mass is 850. We're using 10 for acceleration. And the height is 140. And we get a lot of energy. So 1,190,000 joules of energy. And that'll be our total. By the way, 850 kilograms, that's almost a full ton in pounds. Maybe 0.75, three quarters of a ton. Yes. Now this is where The reason why, so remember, this is only constant if there's no friction. Let's see if we can actually solve this right now. What is total mechanical energy? It's the sum of your kinetic energy and your potential energy. So what's our kinetic energy at point D? Let's say we started at D. You come to a stop at D. So what's your kinetic energy? 0. And our potential energy is mgh. So we can solve for C and D. C and D will have the same potential energy, yes. Yes, velocity is going to be 0. So our potential energy at C and D would be the mass 850 times 10 times 80. So our potential energy is 680,000, and that's the same for here, right? Because it's here, it's just mass times g. Our height doesn't change, so that's also equal to 680,000. But now let's look at the total mechanical energy at D. 0 plus 680,000 joules. So what happened to this total mechanical energy? It decreased. Where'd it go to? Where'd the energy go to? Heat. So have you ever slammed on the brakes and then went and felt your brakes? If you did, you probably got a third-degree burn because they can get actually so hot they start glowing. And y'all put your mask, Thomas, mask, Cody, and Michael. Yeah. So this energy here is lost, or this mechanical energy. Again, this is mechanical energy is lost due to brakes heating up. But we can still assume that this is frictionless between A and C, and we can solve for some variables. So let's go ahead and what will we do next? So C, we can solve for kinetic energy. So this minus that is 510,000. I like solving for all the energies first, after doing our given variable, solving for all the energies. So let's solve for, we don't have velocity, so we can't do kinetic, so let's do our potential. That's potential energy is mgh. So 850 times 10 times 95. So 8,000, or 807,500. Where'd you get the 50? $850 times 10 times 95. Now we can solve for kinetic energy. So kinetic energy is equal to total mechanical energy minus potential energy. So this minus that, and that'll give you 382,500 joules. Now we can solve for the velocity. The velocity is equal to the square root of 2 times the kinetic energy divided by mass. So that's 2 times this, 382,500 divided by the mass of 850. That gives us exactly 30 meters per second. Nice even number. We can do the same thing for the velocity here. So square root of 2 times 510,000 divided by 850. And we get a value of 34.641 meters per second. So the question asked, how fast is a roller coaster moving at point B? Well, at point B, it's moving 30 meters per second. Then it says, what is the average force that is required to bring the roller coaster to a stop at D if the brakes are applied at point C? So we assume that the brakes create friction and that we're slowing down due to the friction of the brakes being applied. How will we solve for the average force? What is force? Mass times acceleration. What is acceleration? Yeah. VF VI divided by. I forgot to give you all time. Let me calculate it. Bueno. Yeah, that's because it uses more advanced physics than I'm doing right now to get you that. I'm going to erase that and give you a time instead of distance. So I'm going to add this, remove the 120, and put that the time between here and here took 6.9282 seconds. The roller coaster stopped in 6.928 2 seconds. Uh, 9282. Now we can plug it into this equation. I didn't check beforehand that this used distance, not time. So we can plug this in now. The mass is 850 kilograms. The final velocity was 0. The initial velocity is whatever speed it was going at point C. So 34.641. And our time was 6.9282. So our initial velocity was 0 at point D. Our final velocity is 0 at point D. Our initial velocity at C was 34.641. And it took 6.9282 seconds. And we get a value of negative 4,250 newtons. It's negative
because it's indicating that the friction force is opposite to the direction the roller coaster is going. Does that make sense? We just used some previous stuff. This isn't going to be on the test. I'm not going to retest I'm not going to have anything complicated like this. I just wanted to introduce that in there some systems we can assume that it's frictionless up to some point, and we can get a really good approximation. And then we can apply friction at the end to get the final answer. So these brakes have to generate over 4,000 newtons of force in order to stop it in less than 7 seconds. If you were in the real physics class, we would use more advanced calculations to actually have it stop within 120 meters, but that's outside the scope of this class. We only know how to get acceleration using Vf minus Vi over T. The real physics class is more advanced, and we actually have other equations to get it. It just requires a significant amount of algebra. Everyone good? I mean, it's pretty simple, I think. You just keep asking, what is the mass at A? What is the acceleration at A? What is the height at A? What is the velocity? Keep asking these questions for the first part. Then calculate kinetic energy. How much time do we have? Hand them in. I'm going to hand it right back. I just want to make sure that y'all are taking notes. Good. Good. Turn it over. Good. Flip through it. Good. 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 She went to the bathroom, but she's good. Oh, good. Here's the code word for the day. I have plenty of time left. Let's solve the quiz together. Yeah. Let's see how simple it was. Alright. You don't have to take notes during this portion. We can just work on this together. So what do we do first? So the mass, 50 kilograms. And that stays constant. All the given. So we can plug this in. Alright. So what's the height at A? What's the height at B? Height at C? Height at D? It's cut off, but it says at rest. So what does at rest tell us? I have these switched around. I'm actually going to keep it consistent. I usually write kinetic energy first. So kinetic energy is 0 joules.
We can also come over here to this 0. 0 meters refers to a potential energy of 0. And now we can solve for potential energy. It's mgh. Oh, C is given. Good point. 11. So mgh, 50 times 10 times 10. And so the total is, and we can write this across the board. So what's next? Alright, so 50 times 10 times 5. 2,500. For D, so velocity is equal to the square root of 2 times kinetic energy divided by mass. So 10,000 divided by 50. So 50 divided by 10,000 is, so that'd be 1,000 divided by 500. It's 2,000, right? That's not 2,000. That's 200. The square root of 200 is 14.1421 meters per second. We can do the same thing velocity over here. Velocity is equal to square root of 2 times kinetic energy divided by, so 2, that's 5,000 divided by 50, which is the square root of 1,000. That doesn't seem right. 100. What's the square root of 100? 10. So that's 10 meters per second. Well, we can get kinetic energy here, right? Kinetic energy is equal to what? So yes, 1/2 mv squared. So half of the mass is 25 times 11 squared, 121 times 25. So that's 3,025. Then we subtract. And then height. Height is equal to potential energy over mass g. So that'd be 1975 divided by 50 times 10. That's 3.95 meters. I guess we will stop here. But once you've worked on this a few times, isn't this really easy? Alright, that's it for today.